Welcome to part 3 of 4. DC brushless motors should have a safe amp rating of 1.2 times the maximum current delivered to the motor. In this particular case, 60 amps DC is the maximum current delivered into the motor. Therefore, the safe amp rating of this motor will equal 1.2 times 60 to equal 72 amps. This 3000 kV DC brushless motor without the fan attached would have a no-load RPM equal to the no-load voltage, which is calculated by taking the wattage input to the motor of 1278.7 watts and then dividing it by the amps, in this case 60 amps. That would equal the no-load voltage, then multiplied times 3000 kV to equal 63,935 RPM when the throttle is set at maximum power. Now that the physics and mechanics pertaining to the fan under a load have been accurately quantified, moving on to the propulsion mechanics is next. At maximum throttle, the effective voltage that remains after factoring out all efficiency losses is a load voltage of 13.64 volts DC. To calculate the airflow propulsion mechanics involved, we can start with the fan's rated inches pitch, which in this case is 3 inches of mass airflow displacement per 1 revolution of the fan. So if we find out what the revolutions per second are at 40,920 RPM, we simply divide that RPM into 60 seconds, and then after we calculate the revolutions per second, in this case 682 revolutions per second, we then multiply it times the airflow displacement in feet per revolution, which is 3 inches divided by 12, or a quarter foot, 0.25 feet. When we do so, we calculate at 40,920 RPM an intake duct airflow velocity of 170.5 feet per second will occur when the fan is rotating at 40,920 RPM. Then we take that airflow velocity through the intake duct and multiply it times the intake duct cross-sectional area. In this case, 170.5 feet per second times 0.05 square feet intake cross-sectional area will equal 8.5 cubic feet per second airflow flowing through the intake duct. 8.5 cubic feet per second will flow through the intake duct when the RPM is at 40,920 RPM on the fan. Previously, we calculated the intake to inlet pressure ratio. Since going from the intake to the inlet is a divergent nozzle, the pressure ratio will be obviously below 1 by dividing the cross-sectional area of the inlet by dividing the cross-sectional area of the intake to the inlet, 0.05 square feet, into 0.068 square feet, we get an intake to inlet pressure ratio of 0.735 to 1. Knowing that, we can then calculate what the actual airflow is at the inlet now that we have the intake airflow velocity. By multiplying 170.5 feet per second, the airspeed at the intake times the pressure ratio in relationship to the inlet of 0.735 to 1, we calculate an airflow velocity at the inlet of 125.3 feet per second. Then, multiplied times the cross-sectional area of the inlet, 0.068 square feet, we also calculate 8.5 cubic feet per second airflow. It has been proven that the constant volumetric airflow ingested when at maximum power is 8.5 cubic feet per second at both the inlet and intake ducts. This constant volumetric airflow will then accelerate out of the exhaust at a higher velocity while the EDF unit is held at rest, resulting in static thrust. Assume that the given 90mm EDF is operating at an elevation of 880 feet above mean sea level in 62° Fahrenheit air temperature. The next step is to solve for air density in pounds per cubic foot. So we can go and access the atmospheric pressure in pounds per square inch formula between mean sea level and 36,089 feet above mean sea level using this formula here, simply entering in 880, dividing it by this value, subtracting it from 1, this entire quantity then taken to the 5.255876 exponential power. Then whatever that value equals, multiplied times 14.7. So at 880 feet above mean sea level, the atmospheric pressure will be 14.24 pounds per square inch. Then that value, atmospheric pressure, PSI, multiplied times 29, then divided into the quantity of 10.73, the ideal gas law constant for air, multiplied times the absolute temperature in Rankine's degrees, which is equal to Fahrenheit plus 460. In this case, when we do so, we get an air density of 0.0737 pounds per cubic foot when at an elevation of 880 feet above mean sea level and 62 degrees Fahrenheit air temperature. So now we know that we have this constant of 8.5 cubic feet per second when at maximum power setting, multiplied times 0.0737 pounds per cubic foot will equal 0.6 pounds per second of mass airflow when at maximum power setting, or 40,920 RPM. So that translates to an inlet duct airflow velocity of 125.3 feet per second and an intake duct airflow velocity of 170.5 feet per second. As previously, we calculated the inlet to exhaust pressure ratio of 1.54 to 1. So all we'd have to do is multiply the inlet airflow velocity of 125.3 times 1.54 to calculate the jet velocity. And in this case, when we do so, the jet velocity will equal 193 feet per second. Jet velocity represented by V2. Now we have all the information to calculate the maximum static thrust output when at maximum power. Simply take 0.6 pounds per second mass airflow multiplied times 193 feet per second jet velocity, then this quantity divided into 32.2 feet per second squared, which is the gravitational acceleration on Earth. When we do so, the maximum static thrust output at maximum power will equal 3.6 pounds of static thrust. The additional thrust developed by the fan as a propeller is approximately equal to the pressure greater than atmospheric pressure that is exerted against the fan disk area on the lower surface area of the fan blades exerted forward. So pressure is a ratio between the amount of force applied to a given amount of surface area. The inlet duct cross-sectional area is equal to the fan swept area, assuming blade tip clearance between the inner wall of intake duct is 0. The cross-sectional area of the intake duct in square feet needs to first be converted to square inches. So the intake duct cross-sectional area of 0.05 square feet, if you take the square root of that, you will get a linear feet of 0.22 feet multiplied times 12 to get inches, then squared. 0.05 square feet will equal 7.2 square inches. So next we take the mass airflow in weight pounds per second and convert it to kilograms per second by dividing 0.6 into 2.2. So 0.6 pounds per second is equal to 0.27 kilograms per second mass airflow. Acceleration is the change in speed, not the speed, but the change of speed, either acceleration or deceleration, also known as negative acceleration. So we want to calculate what the actual acceleration is as the airflow increases in speed from the inlet to the intake. So all we'd have to do is convert all of these velocities at the inlet and the intake into metric values for velocity or meters per second. When we do so, we calculate a speed increase of 13.8 meters per second of the airflow when it goes from the inlet to the intake. Since that speed change is happening over 1 second time standard of acceleration, the change in speed of 13.8 meters per second divided by 1 second will equal an acceleration of 13.8 meters per second squared. So now we can calculate the actual additional force that will exert against the fan disc area by taking the mass of 0.27 kilograms of mass air times 13.8 meters per second squared. So a force greater than the pressure from atmospheric pressure times area. The force greater than atmospheric conditions of 3.7 newtons force will also exert on the rear faces of the propeller disc area forward. So force is pressure times area. So now that we know that we're also developing a forward force of 3.7 newtons, we can then divide that into 4.45 to get the pound force approximation exerted against the disc area of the fan. But we also need to prove this to make sure that it is correct. So we can go back to the pressure formula once again and take the force we calculated from the mass airflow acceleration from the inlet to the intake fan swept area, 0.8 pounds of force, and then simply divide that by the fan swept area of 7.2 square inches, which is also equal to the intake duct area. When we do so, we get a precise value of 0.11 psi greater than atmospheric pressure. So we round that down for accuracy, going from precision to accuracy, we round it down. So 0.1 psi above atmospheric pressure times a fan swept area of 7.2 square inches equals 0.7 pounds of additional thrust by the propeller. So the propulsion static thrust at max power is 3.6 pounds of static thrust. The additional Bernoulli's propeller thrust will equal an additional 0.7 pounds. So if we want to calculate both the Newtonian and Bernoulli static thrust when at maximum power, we simply take 3.6 pounds and add it to the 0.7 pounds at the propeller or fan. So we have a total static thrust including both mass airflow acceleration and pressure times area, Bernoulli's force, at the propeller disc or fan, equaling a total of 4.3 pound static thrust. Based on the given specifications, maximum available DC electrical power, and calculated efficiency losses, this given 90 mm electric ducted fan propulsion unit will approximately develop a maximum static thrust of 4.3 pounds and a jet velocity of 193 feet per second when operating at maximum power setting while the motor or EDF unit is held at rest. If this 90 mm EDF propulsion unit was installed onto an RC flying wing with proper wing loading and weight limitation, flying at level altitude while at maximum power, its top speed limit would be limited by the aerodynamic drag of the airframe and the EDF unit's jet velocity. Ignoring aerodynamic drag, the law of conservation of momentum would limit the maximum flight speed at level altitude to that of the jet velocity. This is because a jet-propelled airplane cannot fly faster than its jet velocity. But when the aerodynamic drag component is factored into the calculation, the airplane's top speed is further reduced. Aerodynamic drag is the force which opposes thrust. The four forces acting on an airplane in flight are thrust, drag, lift, and weight. Aerodynamic thrust is the force pushing the airplane forward, whereas aerodynamic drag is the force pushing the airplane rearward. Airplane weight is the downward force of the airplane as mass accelerated by gravity towards the Earth, and aerodynamic lift is the combined Newtonian and Bernoulli force upward opposing weight. Suppose the given RC flying wing has the following airframe specifications. Leading edge projected wing area 36 square inches. Fuselage nose cone projected frontal area 13 square inches. Air density in slugs per cubic foot, we would have to convert pounds per cubic foot air density to slugs per cubic foot air density. Since there is 0.031 pounds to, since there is 0.031 pounds weight, which equals one slug, we would simply take the air density of 0.0737 pounds per cubic foot and multiply that times 0.031 pounds to equal one slug, and that pounds per cubic foot would be converted into 0.0023 slugs per cubic foot air density. This air density in slugs per cubic foot would equal the existing air density we calculated earlier. Next, the wing aerodynamic drag coefficient for a flat airfoil is 0.09. The fuselage nose cone aerodynamic drag coefficient is 0.5. And then the aerodynamic drag in pounds formula is the drag coefficient times the air density in slugs per cubic foot times the projected frontal area in square feet times the airspeed in feet per second quantity squared, then this entire calculation divided by 2. That will calculate the drag in pounds opposing the forward motion and thrust of the given airplane. So these have all been defined here. Also, 1 square foot is also equal to 144 square inches. This is an easier conversion factor to use in the formulas to save some time. So net thrust or dynamic thrust is equal to the difference between the jet velocity and the forward flight speed in feet per second. Whatever the difference is, then multiply times mass airflow in pounds per second, and then this entire calculation divided by gravitational acceleration on Earth, 32.2 feet per second squared. So that's the dynamic thrust or the net thrust. This only exists when the airplane is moving. When the thrust output exists and the airplane and motor are held at rest, then there is no net thrust, it's only static thrust. So since we're moving here in flight, this would be a net thrust calculation, which is simply just the difference between the jet velocity and the forward airspeed in feet per second. Net thrust, also known as dynamic thrust, refers to the available thrust when the jet propulsion engine or motor is moving through the air during forward flight, unlike static thrust, which refers to the thrust output when the engine is held at rest. Notice that net thrust is the difference between the jet velocity and the forward flight speed, then multiplied times the mass airflow, and then divided into gravitational acceleration. This will end part 3 of 4